Hello, everyone, and welcome to the Midweek program at the Raulston Arboretum. My name is Blake, and I'm the Education Assistant here at the Arboretum, and today we are in the Asian Valley, tucked up underneath some big old banana trees that are vigorous and they're just enormous. We got a program for you today, why Asian plants do well here. Banana trees aren't the only Asian species that do well here. We've got this whole garden full of Asian species that are happy as can be, and we've got our curator, Carey here, who's pulled together a little presentation that's going to go into great depths explaining why that is. So it should be an absolutely wonderful program.
Yeah.
Those of you joining us on YouTube, please like this video and subscribe to our channel, and feel free to leave a comment down below. And with the announcements out of the way, I can pass things over to Dennis to tell us a little bit about why Asian plants do so well here.
Sure, let's do that. Let's talk about Asian plants. I'm going to go ahead and share my screen now. So this lecture came about as a question from one of our volunteers, Carol Lawrence. I hope you have your internet back and are watching, because this is an answer to your question. Why do Asian plants grow so well here in the Southeast US? We have lots and lots of Asian plants. We're in the Asian garden, which is just one of two gardens that feature Asian plants here at the Arboretum. And when we're talking about Asian plants, we are talking about Eastern and Southeastern China. We're talking about Southern Korea. We're talking about Japan, large areas of Japan. We're talking about a certain range of plants in Taiwan. And even Mark has been to Vietnam and gone to the very north part of Vietnam, right up by the Chinese border. And there's mountains up there. Son Pa is a village in there. It's about 6,000 feet elevation. And there are plants that you can get there in Vietnam that will barely eke out a living here. There's a lot of different Asian plants that grow here, and we feature them all in Asian Valley. But we also have another garden that features Asian plants. We have a Japanese garden. Now this is more of a meditation garden, a Zen garden. It's a place for you to go. It'd be a great place to forest bathe. You go in there and you relax. And it's not about bright colors. It's about serenity and textures and that sort of thing. But so we have two gardens in our small arboretum here dedicated just to Asian plants. But we have Asian plants mixed throughout the entire garden. And I did a rough count today in our computer, and we have over 3,800 of our, call it 10,500 or so plants in the living collection.
But who's counting?
Yeah, who's counting? Well, the number goes up and down every day. So, you can only talk in generalities, but 3,800 of them are Asian. So that's a really large percentage. And what are the reasons for that? That was Carol's initial question. Carol, if you're there, I'm gonna basically give you kind of two answers. They're sort of related. So I'm gonna go off and do some kind of science nerdery. And then I'm going to come back and we'll see some of these Asian plants and their American counterparts in the garden.
We love your science nerdery, Dennis. We are all ready for it.
Good. All right, so thousands and thousands of Asian plants grow well in the Eastern US. And we know these, we love these. We grow them almost as if they were native themselves. They have Japanese maples, of course, any number of different camellias. This one here is a autumn blooming variety of Camellia hyemalis. Forsythia is Asian. Peony, lactiflora, Asian. Although there are peonies from other places as well. Aspidistra, great shade, evergreen ground cover, Asian. Ginkgo, who loves ginkgo? I'm staring at a beautiful ginkgo right here. I can't wait for it to turn yellow like this photograph. Asian, and Buddleia, or at least Buddleia davidii is a Chinese plant. There are Buddleias from South America and other places as well. And but the big one that we grow in our gardens is Buddleia davidii, a Chinese plant, and thousands of others. So why so many? All right, well, let's first of all, let's talk about how many species these Asian countries have and compare them to ours. So China, which is a little bit bigger than the US, it's about 5% larger than us, has over 30,000 plant species that grow in it. And that's way more than us. The United States, I have a slide in a second, has and if you include Canada, everything north of Mexico and North America is a little over 20,000 species. So China is significantly more. And there are some reasons for that. In China, you have this unbroken continuum of boreal, temperate, subtropical, and tropical spaces where species can move up and down, north and south, and can interbreed and stuff like that. So you have greater levels of speciation. And then also, we'll see in a few minutes when I get to that slide, they were less affected by the glacial periods than North America was. And the glaciers did drive a lot of extinction in North America. So we're sitting at 20,000 in the United States and Canada, and they're above 30,000. Japan, we have a lot of Japanese plants here. Japan isn't that big, comparatively speaking, huge population, but the country itself is the size of the state of California. It's a very long, skinny country if you include all the islands down south and the islands up north. And so it goes, its latitude varies basically from, southern Florida, the Keys, all the way up to Maine. So, it has a very wide range. It's a very mountainous country. And so you have a wide range of climates in the mountains. In fact, mountains are a good substitute for latitude. Every 1,000 feet that you gain in a mountain, you go up 3 degrees Fahrenheit, or down 3 degrees Fahrenheit rather. So, you have to travel a lot further than that flat north to lose 3 degrees Fahrenheit. So mountainous countries are good because they have these bands or zones within the mountains that match a lot of different climate zones. Korea, and I have two icons here. The big one is for South Korea, because we know more about it, and then the little one's for North Korea. North Korea, we don't know very much about its flora at all. The flora of Korea wasn't very well known until the 20th century, and we've had some notable folks go and botanize out there and bring back collections, including JC back in '85, I think. Yep. And so Korea is a tiny little place. The whole peninsula is the size of Pennsylvania, but it's got 5,300 species. And it's got a lot of mountains and a lot of climates that cause on that peninsula a mixture of both northern and southern plant types. Right near the word Korea on this slide is an island. That's not a typo or a speck on your screen. That is the island it's called Jeju Island. Jeju Island's small in area, less than 1% of the area of Korea, but it has 60-something% of its native species on it. It's incredibly botanically rich. And a lot of those islands down there off the coast of South Korea are incredibly botanically rich. And a lot of the plant collectors, when they go to Korea, they end up getting on boats and going from island to island. Okay, Taiwan, even smaller. This is about the size of Maryland, and it's also very far south. Taiwan on the coast is quite tropical. Okay, but it is also another one of these places, very mountainous. It's 14,000 feet at its highest point in the middle. And so you can go from tropical all the way up to 14,000 feet and then back down again. And so again, we have this area, these zones where there are plants that grow very, very well in the Southeast US, these zones in the 3,500 to 6,500 foot elevation that grow great there. So when Mark does his plant collection trips to Taiwan, he doesn't hang along the coast. And he doesn't go to the tippy tops of the mountains either. Those are alpine. He goes to the particular elevation zone, depending on what part of the island he's on. So here we go. The US, 17,000 species, 20,000 if you include Canada. The Southeast US is unusually rich in species. Over 11,000 plants call the Southeast US home. So that's great. One of the reasons we have so many fewer species than China is China was less affected by the glaciers. I think I already mentioned that, but the little blurb popped up here. So
sure.
Worth mentioning again. So I tried to line up, we have similar latitudes, okay, and attitudes of Eastern Asia. I tried to, on these two maps, I tried to line up the 30-degree line. So the 30-degree line in China goes through Wuhan. It's just a little bit south of Japan. The 30-degree line in the US is northern Florida, Louisiana, south central Texas, that kind And then the 40-degree line in the US is Pennsylvania, central Illinois, and that is roughly around where Beijing is. So, and you can see a lot of the places I mentioned, South Korea, Japan, are in that latitude range of the Southeast US. Now, of course, Taiwan is way down south, and actually northern Vietnam is even a little further south. But so we do have similar latitudes over large areas. That counts for part of it. We have similar topographies. We have mountainous regions and Piedmont regions. And we have similar rainfall, although that part of Asia is influenced by a monsoon type climate.
Sure.
But overall, their rainfall for the whole year, you can see, and on this color-coded map, is somewhat similar in the, we'll call it 100 centimeters to 200 centimeters range, depending on where you're at. And if you look at the Southeast, although there are times this summer, it sure didn't feel like we were going to get 100 centimeters for the year. I think we certainly made up for it in
we got it all at once.
September and July. Yeah. Now, leave it to the Germans to kind of classify all this. All right. So if you take temperature and latitude and rainfall, and you look at what species, what type of vegetation lives where, about 100 years ago, this German guy Koppen took all this information and came up with a classification system. And this again he was a botanist, so this was for botanical reasons. And another guy came in behind him named Geiger and modified it a bit. So today it's called the Koppen-Geiger Climate Classification Scheme. And I'm going to put up a color-coded map of that. And all you have to do is match the colors to see that the Southeast US matches very, very well with parts of Taiwan, parts of Eastern China, parts of Japan, the southern tip of Korea. And of course, if you're a zone stretcher like we are, and some of you probably are, you can get some of those northern Vietnam plants and get a little bit out of the climate zone and baby those plants along, and you can get them to survive. So the Koppen-Geiger classification, actually, this is a color-coded map, but what it is they use it's a letter system where it's a 3-letter system where they use, like we are CFA, that's what that chartreuse yellow is, which means we're a temperate climate with no dry season, although it feels different than that sometimes, and a hot summer, which I totally agree with that one. So, and so this kind of map is very useful in determining what kind of plants will grow where, because it was created by botanists for botanists. In fact, when we do our index seminum and some other reporting that we do to other botanic gardens, we will mention, hey, we are a CFA, Koppen-Geiger zone garden. So that's one of your answers, Carol, is yes, indeed, we do have similar climate zones. There's another answer here, and there are certain genera of plants that exist in the Southeast US, and they have cousins species that exist in Eastern Asia, and the very, very few, or if any, relatives in between the Eastern US and East Asia, which is very interesting. There was a very early recognition of the similarities between Eastern Asian plants and Eastern United States plants. One of the first generation of scientists to study plants out on worldwide scale, to have collections that span the world, would be in the mid-1700s. Linnaeus would have been one of them. And he was the first person to have written about this similarity in 1750 here in this publication here, where he basically says, here are some interesting things that are found only in Eastern North America and Eastern Asia. Now, in this case, he's talking about Eastern Canada and Eastern Siberia for these particular species in this document. And then he lists a handful of species down there. And that kind of is like, that's interesting. Why the same genus exists in these very distant places with similar plants. Why is that? He had no idea why at the time. They wouldn't figure that out until 50 years ago. Later, scientists were also noticing this and writing about it. And this guy here, Thomas Nuttall, who was a botanist who was working in the US, had traveled all over the US looking at plants and was familiar with European and Asian plants as well. And he wrote the first genera of North American plants in 1818. And in that book, he says basically, yes, there's this odd distribution of these very similar plants in widespread places, but we don't know why. The science is not there yet. And then later on in the book, when he's talking about the genus Chimaphila, he says, oh, here's this one that's in North America, and there's probably another one of these in East Asia too. All right, so he's already anticipating that sort of thing. And then later on in the 1800s, Asa Gray, who was an extremely famous American horticulturist, made a bold claim, and it kind of followed him for a long time, actually. So between 1840 and 1878, he was writing letters back and forth. He was a cohort of Charles Darwin, and he and Darwin were writing letters. He was the guy, Asa Gray was the guy who brought Origin of the Species to the US and publicized it and this and that. And he was writing with all his other cohorts, and they were all like, yeah, this is so odd. Here we've got these plants that are in Japan that have very close analogs that are here in North America. And what's up with that? So just like Nuttall and Linnaeus and dozens of others before him, he was noticing this as well. But he went on to make a big claim, which was given the term Gray's hypothesis, which basically said that the flora of Eastern Asia is so close to the flora of Eastern North America that that it is closer to the flora of Eastern North America than the flora of Eastern North America is to Western North America. Okay, and so that's a pretty big claim, pretty bold. He had no way of backing it up. There was no science yet, even in 1818 or 1840 rather. But the concept of evolution was coming on board at this time, and so they were starting to feel more confident that yeah, evolution is certainly playing a role in this, and what else is playing a role in this. So modern science eventually caught up. And so, in the 1920s, we had the concept of plate tectonics. It really wasn't adopted until the 60s. And that plays a part in this. And climate change and genetic studies, the knowledge of genes and how the patterns and reading genes and that sort of thing came on board in the 50s and really has grown exponentially since then. And so in the 20th century, we have this branch of biology called biogeography, and its whole reason is to describe why plants are distributed geographically the way they are. And in order to do that, you have to have a knowledge of evolution and how things evolve, and climate change and how species move when the climate moves, and plate tectonics and how land masses move and how that affects water and oceans and other things. And then plant systematics, which is how plants are all related to each other. And once you start merging all of that, you get this field of biogeography. And you get kind of an answer to this second question, is why are there so many of these Eastern Asian species that are so similar to the Eastern North American species? They actually put a name to it. The name of Eastern Asian species being similar to Eastern North American species, they call them tertiary disjunct floras. Okay, flora, we can understand, that means group of plants. Disjunct, what that means is they live in two widely separate places with nothing in between. Tertiary is actually a geology term. It's referring to a time period, basically 65 million years ago to about 15 million years ago. We are now in the Quaternary period. And so what they're saying is once they started figuring this out, they're like, oh, all of this happened 50 million years ago. And so we're going to call these tertiary disjunct floras. And these species, when they refer to them, they call them relict species. So you have a plant that, Erycema in North America, and you have Erycema in Asia, and they are relict species of an ancestor or ancestral group that lived somewhere else and had to migrate into Asia and into Eastern North America, and become isolated there for some reason. And the reason was cooling climates. So we're going to start our story about 50 million years ago. But the cooling part of it, and where this migration mostly happened, was in the last 15 million years of that 50 million years. The climate started cooling slowly until about 5 million years ago, and then it started cooling rapidly. And then that was about the time that the Isthmus of Panama connected North America to South America, interrupted all the ocean flows, and the weather all went crazy and got cold. And it triggered off the glacial period. So this cooling period forced these species that had evolved in a warm place way up north. Well, that warm place was no longer warm, and they had to move, and they moved to a place that was just as warm as it was way up north, still that warm, and that's where they ended up. And those regions are called refugial regions, or Refugia. And to date, we don't really talk about numbers of species here. When we're talking about these groups of plants, these tertiary disjunct floras, we are talking about genera. We speak about them at the genus level or the family level, but not the species level, because the species all evolved after the fact. Other species earlier on, progenitor species, were up in these earlier northern warm areas. Today, we know of about 120 genera of plants that have disjunct populations in Eastern Asia and Eastern North America. Okay. Now, there are actually 5 of these Refugia regions. Eastern Asia and Eastern North America are 2. There are actually 5 of them. I'm going to show you in a map here in a second. But the North America, East Asia one is the most common disjunct group. All right, so here's the map. These colored regions are these refugia or refuges, where these disjunct species ended up after migrating from places further north. So you can see Eastern North America from Florida all the way into southern Canada. And then Western North America is one of these refuges. Right along the coast, it's, you think of the Pacific Northwest and the kind of coastal climate, not the interior climate. Mm-hmm. Eastern China, you can see there in pink, and that includes northern Vietnam as well. And actually, since they've refined this, they're now defining 2 refugial regions in Asia, one in Eastern China and one in the Korea/Japan area. Okay, and then a 5th one, very interestingly, is in and around Turkey. So you have Turkey, you have the Caucasus Mountains and the Transcaucasia, and you have the Balkan Peninsula, Greece and Serbia and Montenegro and Croatia and all those places ended up being one of these other refugia as well. And here in these 5 places, you find species that are in genera that are with widely disjunct gaps in between them. So how did they get there? Well, this map is also showing some of the land bridges that have occurred. Now, these land bridges, they're just shown as colored bars on this map. This is a modern map. This is not where the land masses were when the movements were occurring. So we're going to see better maps coming up. But so there are land bridges, and the one we're going to talk about, I don't know if you can see my cursor on the screen. Can you? Yep. Okay. Is this one over here that where it connected Asia to Eastern Asia to Western North America. It's called the Bering Land Bridge. Right today, it's the Bering Strait, where you can see Russia from your house if you're located properly. And that's a Sarah Palin reference. We're in political season, so
yeah, right.
And that's where a lot of our Asian disjunct species, how they got over to North America, is through the Bering Land Bridge. Also called Beringia, by the way. They actually gave a name, like a country name to it, Beringia. Huh. It was quite large when it was at its maximum extent. So, and then there's, if you see Greenland connects North America to Europe here via land bridge. And actually there's actually several land bridges between Greenland, North America, and Europe that occurred on and off during this time. We're not really going to talk too much about those, though. Beringia is where we're at.
Gotcha.
All right, so let's settle ourselves in time here. If you're a geologist, you come up with this geologic time period chart, which is based on cores going down into the earth and where they see big differences occur. And you can actually overlay that with things that are happening in biology at that same time. And so we are really talking about the Cenozoic, the last, which started 66 million years ago when that meteorite hit the earth and knocked out the dinosaurs, and caused a whole nother layer of geology to occur. So they put a boundary there. But the first land plants showed up about a little over 400 million years ago. The first forests were about 350 million years ago. These were fern forests and proto conifers, not flowering plants yet. Pangea, which plays a part in our story, forms about 330 million years ago and breaks up about 230 million years ago. So it wasn't together terribly long. Well, 100 million years, which actually is terribly long.
It's a drop in the bucket.
just feels like it was short. And then the first flowering plants came up about 135 million years ago. But our story is really in the last 50 million years. So if we blow that up, and look at the area that I've got with a dotted circle around it, our story starts 50-ish million years ago in the Eocene and continues to today. So 50 million years ago, the climate was quite warm, way, way warmer than it is today. In fact, we are in a very cold period of Earth's history. I have a temperature chart coming up. And there were times during the Eocene and where the temperature was so hot that if you were way up above the Arctic Circle, way up in North Greenland or Baffin Island, Canada, or North Australia, or Alaska. Why did I say Australia? So you were so north, you were south. North Alaska. The temperatures there were equivalent to what Florida or North Carolina is today. Okay, it never froze. It was warm in the summer, hot summer, humid weather, lots of rain. So you had the plant species that were evolving up there in the 50 million year ago time frame were evolving in this really warm place. And you have this gradual cooling period that forced them to move. All right. So real quick, here is Pangea. We mentioned it already. This is just after it broke up. You have to imagine Eurasia and North America fused together. So any plants that formed in one spot could theoretically go to all of the continents then just through regular wind or land animals carrying them or whatever. 100 million years ago, you can see the Atlantic Ocean is barely there. Europe and Asia are separated by a big ocean there, almost a sound kind of thing. And Asia is starting to connect up to North America. North America is also bisected by an ocean. 50 million years ago, where our story starts, and this map doesn't show it well. I have some maps coming up that show it better. The connection between Asia and North America is pretty solid, and the plant species that are up there in that northern area can move back and forth over the Bering Land Bridge from North America to South America. You can also see Europe is pretty close to Greenland, and there would be land bridges between Europe and Greenland and North America, and then today. So 50 million years ago is where our story starts. So we're gonna look at another map, and here we're looking straight down on the North Pole. So this is a better way to look at it because you don't get that distortion that you see when you look at a map straight at America. And what you can see here 50 million years ago, you have the Bering Land Bridge up at the top, and you can see Europe, that little island Europe, that's Scandinavia. And then what would be the British Islands would be kind of on the south, that bottom of this view. That little red star, I got this image from a paper, and they were talking about what was that's Baffin Island roughly today, what the weather was like there. And it was quite warm. It was ice-free all year round. It had primates and reptiles living there. It had a swamp, cypress, broadleaf floodplain forest. So it was very much like down east in North Carolina.
Yeah.
Nice and warm. And here we are above the Arctic Circle 50 million years ago. You can't look at any of these maps and say this is how it was the whole time. These maps are constantly moving, not just because of plate tectonics, but because of weather changes causing the water levels to rise and fall. And so these land bridges we see, Beringia did last a long time, but some of these others would form and disappear and form and disappear many times. And here is our temperature chart. You can see we are talking about the Eocene is our 50 million year ago mark. So if you find the Eocene on that, you can see there was a temperature peak. And it's during these temperature peaks that it's so warm, in fact, that tropical species are growing up there. And so some of the disjunct species we have today that are tropical in nature actually had their start way, way, way up there in Baffin Island, northern Canada, when the temperature was so warm, that was tropical. Okay, but you can see that there was a very slow cooling over 35 million years. And then about 15 million years, there was a more acceleration of the cooling. And about 5 million years ago, a rapid acceleration of the cooling that triggered off the glacial periods that we're in right now. All right, and here's some more of these maps showing Beringia. These are altitude maps of how high up the land is above the ocean. 60 million years ago, so the Beringia, there's a lot of estimates of when it actually formed, and we're gonna say for the purposes of this lecture, 65 million years ago is when it first connected up Asia and North America. That was actually a little bit before the Rocky Mountains came up. They were about 50 million years old. So the Western US was flatter.
And this was again right around the time that the dinosaurs went away.
Yes, yeah. 66 million years ago is when the dinosaurs went away. Yeah,
give or take a million or so years.
Give or take a couple weeks.
Yeah.
And then we have this slowly cooling period. And about 26 million years ago, there's this graph here that measures the rate at which species are crossing the Bering Bridge from Asia to America and backwards, the other direction as well. And it rose and rose and rose, and it peaked in the kind of 25 million year ago range. And then it dropped off very suddenly, and that was, it's cooling, and so it becomes less and less, plants become less and less able to cross this, and it cools so much that we start getting ice up there, and these temperate plants are no longer living there at all. So you see this precipitous drop off. And then, so here's our cooling again. It's the cooling starting 15 million years ago that drives these species that were way up there out of Beringia and down to these refugia that they're in today. And then in the last 2 million years, the glacial period is where, so other barriers arose that keep these refugia apart. So if you think Western US is right along the coast, is nice and forested, but then right inland you have almost desert. And so you have these arid bands forming because of the glacial periods that are preventing species on the west from crossing and mixing with species on the east.
Sure.
So you have these arid areas, you have oceans, the continents are still moving, so you have oceans preventing movement. You have the disappearance of land bridges, so you have water preventing movement, and you can't go north anymore because it's too cold. So you have several things that are defining the borders of these refugia. So the Bering Land Bridge, as far as plant movement is concerned, closed about 5.5 million years ago. It opens and closes during this glacial period several times, one of which humans came across from Asia to America. The glacial period started about 2.4 million years ago, and there's been a whole bunch of them on a 100,000 year cycle. So there's 20, let's call it 24 glacial periods, not just one. At the maximum extent of glaciers 21,000 years ago on this map, you can see that the glaciers go all the way down to Pennsylvania and even further down the Mississippi Valley. But if you look at China, the glaciers barely get out of Siberia. So that's one of the reasons China has so many species today, is the glaciers did not impact them. The topography at that time was not allowing the glaciers to sink down and scoop out, huge chunks of land like it did here. In fact, if you look at 3 million years ago, you don't see Hudson Bay and you don't see the Great Lakes. They were all scooped out by the glaciers. So,
sure.
Yeah.
And China's also got the contiguous landmass where you've got the temperate and the tropical without like islands or stuff. So just lots of space for diversification and evolution to take place.
Yeah, and like if you wanted to get from North Carolina to a tropical area, call it the Yucatan, you have to go through an arid area, which acts as a block, or an ocean, which also acts as a block.
Interesting.
And then we have today, of course. I have to end it. I'm not going to talk about that, though. All right, so What are the forms of evidence we have of these movements? Well, we have cores. This picture is actually cores taken from under the ocean, and you see where there's a sudden color change. That is saying, hey, something significant is happening in this region that is causing a huge chemical change, so much so that the core sediments are changing color, either through pH changes or different types of sediment or this or that. Also in these cores, you can find fossilized pollen or fossils themselves, and you can also find different ratios of chemicals. When a big event happens and let's say species are dying out rapidly, they're releasing carbon, and you have this big push of carbon into the environment, and that ends up in these cores, and you can measure that chemically. Carbon isotopes ratios and oxygen isotope ratios are telling that story. Of course, we have fossils that really tell a good story if you can find them, and so here we have examples of these are species that are no longer up where these fossils were discovered, but used to be there. And of course, ginkgo, metasequoia, and davidia are all Asian species, but here they are fossils found in Wyoming and North Dakota. The ginkgo is recently as 5 million years ago, there was some sort of ginkgos up there.
That's amazing.
Yeah, and with the sassafras, we know that there's a eastern U.S. sassafras albida that is from Canada down to Florida in the eastern U.S., and we know that there's 2 species, one in China and one in Taiwan, and nothing in between. Well, here, halfway in between, kind of getting close to where the Bering Bridge was, is in Washington State from the Eocene, is a no longer existing species, a fossil of a no longer existing sassafras species, Sassafras hespera. So we have all these things are connecting the story together. We also have geneticists working, and they are reading the genes of all these disjunct species from around the world and seeing where the genes are similar and where they differ. And you can make inferences knowing how rapidly genes mutate. You can make inferences as to timescales, as to when things were one thing and then were another. And you can make connections between these disjunct species. This particular chart comes from a paper. One of the authors is NC State's own Jenny Zhang, who is a cornice expert.
Yes, she is.
And
you wanted to say benthamidea because she's got her hands in that.
No, I didn't. And this paper is talking about Hamamelis and Castanea, and it's inferring timelines and directions of movement of these disjunct species from the genetic studies that her lab is doing. All right, now that's our nerdy story. We're going to come back finally, and hopefully I haven't lost too many people. We're going to come back and talk about these disjunct species that exist here in the Arboretum today. You can come here today and see examples of these Eastern Asian and Eastern US disjunct species. And so I'm going to go through a few examples here. And Blake, in the show notes, I've got hyperlinks to a bed map and to the overall JCRA map that has a search feature on it. So you can, what I would do if I were you is search out the genera and see everywhere in the garden we have them, and then we're going to talk a little bit about where the different species are from. I'm not going to cover every possible species. We have far too many in our time remaining. But one of the things you're going to notice on these slides are these little codes, E33 and T08 and A01A. Those are the bed names of where these plants live in the garden. And so one of the links that Blake is going to provide you is a bed map of where these beds are in the garden. Also on these upcoming slides, everything on the left side of the screen are the North American, and everything on the right side of the screen are the Asian species. So we're going to start with Aesculus. That's one of those disjunct tertiary relict species. And so we have the American East Coast, Eastern U.S. Aesculus pavia, Western U.S. Aesculus californica, and then we have Aesculus chinensis as the comparison species. We have all 3 of these in the garden. We have other Aesculus as well. We have several more. I could only put so many on a slide, and but there are others, trust me. Erycema is a favorite. We actually don't have the Eastern U.S. Erycema triphyllum, but if any of you go out on a hike in March and April, pretty much anywhere that's near a stream or something, you will see Erycema triphyllum. It's everywhere. Very cute little jack in the pulpit. Asia has some really cool jack in the pulpits. Lots and lots of them. Bigger ones, smaller ones, different colored ones. And so here's 3 that we have in the garden. Erycema consanguineum. Did I say Acer?
You did. That's okay.
Oh, okay. Hopefully, hopefully you knew what I meant.
Yeah.
Erycema cayusianum and Erycema ringens. We've got a nationally renowned Cerces collection here, so I had to throw in a Cerces slide showing Cerces canadensis, the Eastern North American species, and Cerces 3 Asian species, Chinensis, Triniana, and Chingii. There are more species than that, but again, for space reasons, I only included those. It's worth saying, though, that if you Google Cerces biogeography, you actually find that Cerces did not come over the Bering Land Bridge. It actually came from Europe over one of those land bridges.
No kidding.
Yeah, either the Thule route or the De Geer route.
Sure.
That way. So, but it is another one of these. There's a lot of Cerces species in Asia. There's 2 in North America, and there's actually 1 left in Europe. Campsiprus, it's not just flowering plants. There are conifers and ferns. I don't have any fern examples, but there are conifers as well. Campsiprus thyoides is an Eastern North American species. Campsiprus lawsoniana is from the Western U.S. Refugia. And then Campsiprus obtusa and piscifera are both Japanese. And these are all photos from here in the Arboretum. You can see all of these. Sometimes I include the cultivar name, especially if the color or the form is really strange. Sometimes I don't. All right, Cornus. Here we are back to Jenny Jiang. Cornus florida. Cornus cusa and Cornus alba are Asian. Fagus beech, one of my favorite trees. When you're hiking along, you see these beautiful large silver-barked trees in the winter, and the leaves hang on them for a long period of time in the winter too. So the U.S. species Fagus grandifolia, and then a couple of Asian species also here in the garden. Fagus lucida and Fagus hayate. Hamamelis, witch hazels. Several eastern U.S. species, Virginica, ovalis, and vernalis, and then a couple of Asian species as well, Malus and japonica. And we have other species besides those as well in the garden. Just again, didn't include them for space or time. Hydrangea, we have well over 100 hydrangea taxa in the garden. Many, many, many species. So this is just a tiny, tiny example of that. We have 2 Eastern U.S. species, Quercifolia, the oak leaf hydrangea, and arborescens. And then Serrata, which is a Japanese mountain hydrangea. This is a variegated selection here. And Anomala, which is actually a vine, and that's growing. You can see growing on the wall of our Japanese garden. Pachysandra, great shade ground cover. There's an American and a Asian species. And they both are very similar. Actually, the Asian one's probably easier to find in the trade
sure.
than the American one. When I was a grower, we grew more of the Asian one. The American one took a lot longer to produce, which means why it's harder to find it in the trade. It's a longer crop, but both are very, very similar other than that. Podophyllum, May apples. Again, if you're hiking around in the spring, there are places that are just covered in May apples, and it's a real favorite native species of mine. And then we have but they have some incredibly cool May apples over in Asia. I've shown just 2 here. Podophyllum pleanthum. Those leaves, if you really baby the plant, those leaves can be 2-3 feet across. They're huge in certain places. Here in our garden, where we don't have constant irrigation and this and that, they're much smaller, but they are still very, very pretty.
Oh yeah.
And you have that maroon flower too, which is really cool. And then that spotted one, some of the Asians ones have really cool spotted foliage. This is actually a hybrid called Spotty Dotty.
Spotty Dotty.
Yeah, and it's a Podophyllum delavii hybrid. And Spotty Dotty is a favorite of mine too. I really like that. That one, everyone goes crazy when they see Spotty Dotty the first time.
How could you not love Spotty Dotty?
Exactly. Yeah, the name's great, and it's just beautiful when you see it. It's a smaller one. Polygonatum, we have 3 species of native species of Polygonatum. Here's one, Polygonatum biflorum. It's an American species. We have 3 Native American ones. I'm only showing one. The other two on the right side of the screen I'm showing they both happen to be variegated selections I picked, are both Asian selections. Polygonatum odoratum and Polygonatum macranthum. And a lot of the Asian gardeners love collecting the weird variegated ones and putting them on the market. And we end up with a few of them, and they are pretty cool. Although like tiger stripes, probably incredibly slow. Polygonatum odoratum plurifolium variegatum is faster to produce, and you can find that on the market. In fact, I think we had it in the fall sale.
Oh, sure.
Yeah, much more common. It sells out very rapidly, though. The sassafras, I showed you that fossil of the sassafras leaf that was halfway in between where these two species are native. The U.S. native, Sassafras albidum, eastern U.S. from Canada down to Florida, and Sassafras zumu. This is a picture right outside Blake's office.
Yes, it is.
And that is a Chinese species. And then there's another one that is Taiwanese as well. And so those are disjunct. Tsuga, there's 2 examples of American and 2 examples of Asian species here too. So American ones, Canadensis and Caroliniana. You can tell by the epithets where at least whoever named them thought they were from.
Sure.
Right? So Canada and Carolina, that's not necessarily true. The Canadensis ones tend to have, they're not just Canada. But at the time this was named, that's what was on the guy's mind.
Sure.
I'm not sure who named this one. Seiboldii, that's named after Seibold, the famous Chinese. He was not Chinese. He went to China and did plant exploration. He was European. And then Chinensis from China.
And fun fact, the name Tsuga is the common name for hemlock in Japanese.
Okay.
So the scientific names, that's not a Latin name. That's a Japanese name with some Latin slapped on the end of it in a very
to make it Latin
fashion.
sound. Yeah, that happens quite a bit. And there's and it used to be genus Aster, one of the species that we have. It's now called Maya yomina is the genus name, and that just happens also to be the Japanese common name for the plant. That said, okay, we're going to make this the genus name now. So, yeah. And then the last slide, wisteria. Of course, it's one we love to hate. It's very beautiful. We have a native species, Wisteria frutescens, has 2 varieties. We're showing the larger flowered one, Macrostachya, that we have here. And then we have the rampant weed, which we don't have in the garden anymore. So that's why there's not a bed designator there, Wisteria sinensis. But you go outside anytime in April and anywhere in the middle of the city, you'll see it as a weed growing somewhere, in the suburbs, in the country, everywhere, in the woods, Wisteria sinensis. But we do have a Japanese one, Wisteria floribunda. This particular one has extremely small leaves, and this one is actually also a cultivar. It's called hime, and it's certainly not very vine-like there. It looks almost like a little shrub. So that's our last example of these disjunct species whose genera had a common ancestor way up in the warm Arctic 50 million years ago and were forced to move when someone turned the air conditioning on too cold.
Sure.
So Carol, there's the answer to your question. I hope that's satisfactory. I hope you get your internet back and can see this. So why don't we go take some questions now from the audience?
Let's take some questions. Well, I'll say there haven't been any questions that came in. I assume it's just because of how simplistic the topic was, how easy to understand it was, and the thoroughness with which you covered it all.
I tried to be thorough.
You certainly succeeded.
If you read the show notes, there are papers that are I hyperlink to these scientific papers.
Yeah.
Probably at least 50 of them in the show notes.
I will include all of those links.
Read them all if you want, but actually don't. Just go and type some genus name into Google, like Cercis or Wisteria or something, and then type the word biogeography. So Cercis biogeography, Wisteria biogeography. You'll get right to the paper. Sure. And just read the abstract and the conclusion, and you'll get the gist of the story and where it moved and when it moved and all of that. Okay. And any kind of evidence of progenitor species and stuff like that.
Sure enough. Well, here are some questions coming in. Douglas wants to know, do Asian botanical gardens collect and display plants from the southeastern U.S.?
So, yes, but more, to my knowledge, on a more limited basis than we do. Mark, when he goes over to China to do plant expeditions, he is teaming up with botanical gardens, folks in botanical gardens there. And although he's not carrying a suitcase full of American seeds with him when he goes, he's making connections, and we do occasionally send stuff over, or at least try to. Phytosanitary certificates sometimes prevent that. And that is, in my job as curator and in charge of the index seminum here, is one thing. That's one I really do want to get inside of China and Japan.
Sure.
We did get 1 or 2 index semina from Japan, but and I believe one of them ordered from us as well this year. But I'd really like to see more of that.
Yeah, honestly.
And so, yeah.
That'd be cool. Okay, Marilyn says, was this Arctic region further south 55 million years ago, or was the whole planet just that much hotter?
The whole planet was that much hotter. If you came down to North Carolina then, it would be well over 100 degrees every day all year round.
Sure.
You know, it was just enormously hot and humid, and it was just ridiculous. I would hate to be here.
Yeah, for sure.
In fact, I doubt humans could even survive there.
Sure.
But also, yeah, the continents were moving 50 million years ago. They were the Atlantic Ocean, and so Europe and Asia were much closer, and they were also a bit further south than they were now.
The graph you showed had like a baseline where what the average temperature is nowadays, which was something like 14 degrees Celsius. And it had a bunch of things. At one time, it was up around 30 was the average. So
yeah, and that's 30 centigrade.
That's 30 centigrade, which is hot.
100 degrees Fahrenheit.
It's hot,
and that's global average.
That's global average.
Daytime high, nighttime temperature, summer, winter. You average all that out. Today, you get 14.7 degrees centigrade. That includes our ridiculously hot Julys here and the ridiculously cold weather in Antarctica. You go back 50 million years, and that global average wasn't 14, it was 30. It was double.
No kidding.
So yeah, it's a little bit of both. It's the continents were still moving, and it was a lot warmer.
Awesome. Well, that appears to be all of the questions that we had for today and all of the time we had. This was a really fascinating subject, Dennis. Like, you start studying evolution, you see the interconnectedness of all life on Earth, but then when you tie geology into it and like how the role that plays in moving things around and just how it's all connected all through all of history and all over
these time periods. I mean, you can say 50 million years, but you can't. That is as inconceivable to actually stretch your mind to be 50 million years. And we are actually going back 200 million years to Pangea, and 500 million years for the life on multi-celled life on Earth. Sure. You know, so these are unimaginable times. Yeah, actually, on that little graph, there was a little blip at the right that I didn't mention. That was the entire human species history, all 300,000 years of the human species. Teeny was just this little blip on the edge of that. On the edge of that map. It's amazing. It was all in the cold period. Our species has only existed when the Earth has been relatively cold. Yeah, for sure. So like I said, it's a really simplistic topic, really easy to get a grasp on mentally without much struggle at all. So anyway, I hope. This was really fun. So as a horticulturist, you're introduced to these things, but I got a chance for this talk to do a deep dive. If you get a master's degree or a PhD in plant systematics, this is where you really dive into this subject of plant biogeography in plant systematics. Awesome. My master's is not in systematics. It is in chemicals and things like that. So this was a real fun experience for me. Well, great. I'm glad you had fun with it. I know we all enjoyed hearing from you, Dennis. So thank you so much for preparing this. Yeah, and the audience is going, that's what he considers fun? That's okay. Different strokes. It is. Different strokes for different folks. Different folks. That's right. And thank you, everybody, for joining us on the Midweek program today. We will be back next week. Greg and Tim will be doing bloodthirsty plants because it's spooky season, y'all. We're going to go through plants with pokies and spinies and all that jazz. So it should be absolutely wonderful. We will see you all next time. Y'all take care.